For this reflection assignment, I chose to look at termites and how architects have mimicked their techniques in order to create high energy efficient buildings around the world. As a civil engineer, it is fascinating to me because we are able to copy high efficiency biological processes and apply them to our structures. So what's the problem? The problem is that our buildings are too expensive. We spend so much money on energy in order for our buildings to be suitable and comfortable for all of the tenants. But even with this price tag, systems degrade over time, costing us more money in the long run. Since 1940, the population in the United States has doubled, yet our energy use and energy consumption has quadrupled, and it shows no signs of slowing down. The bottom line is that we are consuming too much energy, and with 39% of total energy being used by commercial buildings, we need to find more efficient ways to power them. In this presentation, I'm going to discuss how architects are addressing climate control within buildings by turning to bioengineering. So, enter the termite. Small but hardworking, these insect colonies create structures for themselves called mounds that can reach up to 25 feet high and sturdy enough that dynamite is required to remove them. These termite colonies are split into two groups, the foragers and the nest. Foragers gather and ingest woody material and then take it back to the nest. From here, nest termites feed it to the Basidiomycete fungi that grow in the nest. These fungi break down woody plant material in order for it to be more easily digestible for the termites. The termites are in a symbiotic relationship with this fungus, and the colony depends on it for their food source. All these guys require lots of energy, and with a high metabolism, the mound requires lots of oxygen. Now let's look at the structure of the mound. The nest is located below the ground. It consists of a central nursery with the royal cell and the fungus gardens. There exists a network of tunnels that merge to form a central chimney, and the chimney extends to lateral connectives, which lead to surface conduits and a porous surface layer. Notice that the nest is completely underground. This is important for maintaining a constant temperature within the nest. The termite mound is out of equilibrium, meaning that the oxygen content is below atmospheric, carbon dioxide is above atmospheric, and the humidity is higher within the mound. Due to the metabolic demand of the termites and the fungus, homeostasis of the mound is achieved by balancing the metabolic demand with the ventilation of the mound. Although termites can exist in conditions with high concentrations of carbon dioxide, the fungus cannot. The mounds must balance the level of ventilation with the temperature of the mound in order to allow for fungus growth. These mounds breathe similar to a lung in the way that they take in oxygenated fresh air from the lower holes of the mound and exhale CO2-rich air from the chimney and upper holes. The air that leaves the central chimney is generally warmer than the air that is being drawn into the mound from the lower holes. The ground temperature continues to keep the nest cool. At night, when temperatures drop from 40 degrees Celsius to 0 degrees Celsius, the ground that's surrounding the nest that has been heating up all day now creates internal thermal constancy for the nest through the night until the morning, in which the cycle starts over. So here's the basic idea. Passive cooling is this idea that you're using temperature gradients in order to maintain this kind of constant temperature so that it doesn't fluctuate even though your environment temperature may be fluctuating. The nest also breathes similar to a lung in the way that it exchanges gas. Most importantly, the termites utilize the temperature absorbance of the ground throughout the day to regulate temperatures even when fluctuations of 40 degrees are occurring. Now let's look how this is being applied to architecture. When Mike Pierce was brought on to design the Eastgate building in Zimbabwe and Council House 2 in Melbourne, Australia, he took advantage of night cooling, thermal storage, and convective air currents in order to moderate temperatures. During the day, the building's large mass and rock storage in the basement absorbs the heat that's collected through the day, both from the environment and human-produced. Then at night, the cool air from outside is allowed into the bottom of the building, and it starts the convective flow that vents the hot daytime air through the roof vents. The cool air from the night is also stored and distributed throughout the building the next day. Looking at the numbers of the Eastgate building in Zimbabwe, it's pretty apparent how efficient Pierce was able to make this building. When it was built, it used 10% of the typical ventilation systems used in a building that size. Monthly, it cuts cost by about 10%, which in this $36 million building, it's saving the building about $3.5 million. Then in the Council House 2 building in Melbourne, Australia, Pierce perfected his technique. Like the Eastgate building in Zimbabwe, this one is cooled by a timely management of the temperature difference between night air and day air. An entire side of the building, similar to the surface layer and central chimneys of the mounds, acts as air intake and gas exchange, as you can see by the wood paneling. Then at night, the warmer air is vented up to the mass of concrete and up through the floors in order to keep the office comfortable until midday, when cool, fresh air collected overnight is slowly released. The concrete absorbs the hot air from the day and releases it at night to once again maintain it through the cold night. The mass of concrete functions like the ground around the nest because it absorbs temperature and heat and then releases it to maintain homeostasis. Thank you for watching.